Imagine a force that is invisible yet powerful enough to shape planets, guide stars, and protect life itself. A force that surrounds us every day, yet remains one of the greatest mysteries in science. We feel its pull, we see its effects, but do we truly understand it? Today we are going to journey into the fascinating world of magnetism, a force that has puzzled the brightest minds for centuries and continues to challenge everything we think we know about the universe. From the tiniest particles spinning inside atoms to the colossal magnetic fields that stretch across galaxies, magnetism is everywhere. Yet its true nature remains elusive. In this exploration, we will uncover secrets hidden in the quantum realm, witness the incredible impact of magnetism on technology and life, and confront the mysteries that push the boundaries of human understanding. By the end of this journey, you will see that magnetism is not just a scientific concept. It is a gateway to understanding the universe itself. A reminder that even in the things we take for granted, there are wonders waiting to be discovered. So stay curious, stay attentive, and get ready to see the invisible force that governs the world in a way you never imagined. Magnetism is one of the most familiar, yet most mysterious forces in our universe. We see its effects every day in the way a compass points north, in refrigerator magnets, and in countless electronic devices. But the underlying nature of magnetism remains a profound enigma. At its core, magnetism is a force that arises from moving electric charges, but this simple statement hides layers of complexity. Electrons, the tiny charged particles orbiting atoms, not only move but also possess a property called spin, which contributes to the magnetic behavior of matter. When these spins align in certain ways, they create macroscopic magnetic fields, like in a bar magnet, yet understanding why these alignments occur naturally in some materials and not others requires a deep dive into quantum mechanics. Classical physics, with its elegant laws of electromagnetism, explains how magnetic fields interact with charges and currents, but it falls short of revealing the root cause of the magnetic phenomena at the atomic and subatomic level. Even more puzzling is the way magnetism interacts with other forces in nature. The subtle interplay between magnetism and electricity, encapsulated in Maxwell's equations, points to an underlying unity in the laws of physics. Yet the quantum world introduces uncertainties and probabilities that challenge our classical intuition. Scientists continue to explore the origins of magnetism, from the alignment of electron spins in materials to exotic quantum states that could one day lead to new technologies. Magnetism is more than a force. It is a window into the hidden structures of reality, a reminder that what we observe on a macroscopic scale is only a small part of the story, and that nature's deepest secrets are often invisible, requiring patience, curiosity, and imagination to uncover. Magnetism is not just a classical phenomenon, it is deeply rooted in the strange and fascinating world of quantum mechanics. At the microscopic level, electrons, which generate magnetic effects, behave in ways that defy our everyday intuition. Each electron possesses a property called spin, a kind of intrinsic angular momentum, which is fundamentally quantum in nature. Unlike a spinning top, electron spin does not correspond to physical rotation but is a quantum characteristic that creates tiny magnetic moments. When many electrons in a material have spins that align, their combined effect produces a noticeable magnetic field, a phenomenon known as ferromagnetism. However, quantum mechanics adds layers of complexity, revealing that these spins do not simply align randomly or predictably. They follow probabilistic rules governed by wave functions and quantum statistics. Even the motion of electrons in their orbitals contributes to magnetism, with their angular momentum generating additional magnetic fields, yet these effects cannot be fully captured by classical formulas. Quantum entanglement and electron correlations further complicate the picture, creating exotic magnetic states in certain materials, such as spin liquids, where the spins never settle into a fixed pattern. These states challenge our understanding of order and symmetry in nature, and suggest that magnetism is not merely a byproduct of moving charges, but a window into deeper quantum laws. Researchers continue to explore how quantum mechanics underlies magnetic phenomena, from the smallest particles to large-scale materials, aiming to uncover principles that could revolutionize technology. Understanding magnetism at the quantum level is crucial, not only for fundamental physics, but also for advancing applications like quantum computing, spintronics, and magnetic storage devices, showing that the mysteries of magnetism are intricately linked with the very foundations of reality itself. Magnetism is not confined to laboratory experiments or technological devices. It shapes the universe on scales both vast and subtle, influencing phenomena far beyond our everyday perception. The Earth itself is a giant magnet, generating a magnetic field that extends thousands of kilometers into space, forming the magnetosphere, which shields life from harmful cosmic radiation and solar winds. Without this protective magnetic bubble, the planet would be exposed to energetic particles that could strip away the atmosphere and disrupt biological processes. Beyond Earth, magnetism plays a critical role in stars, planets, and galaxies. Solar flares and sunspots arise from complex magnetic interactions within the Sun, releasing immense energy that can affect satellite communications and power grids on Earth. Pulsars, highly magnetized, rotating neutron stars, emit beams of radiation that sweep across space, their precise timing governed by powerful magnetic fields. Even interstellar and intergalactic magnetic fields guide the motion of charged particles across the cosmos, influencing the structure of galaxies and the behavior of cosmic plasma. Despite the ubiquity of magnetism in the universe, our understanding of how these large-scale magnetic systems form, evolve, and interact remains incomplete. Observations suggest that magnetic fields are crucial to the birth of stars and the dynamics of galactic evolution. Yet modeling their behavior requires advanced computational tools and sophisticated theories that bridge classical and quantum physics. This cosmic perspective reveals that magnetism is not merely a terrestrial phenomenon, but a universal force that shapes matter and energy across the cosmos, subtly directing processes that determine the fate of stars, planets, and potentially life itself. By studying magnetism on such scales, scientists gain insight into the hidden architecture of the universe, demonstrating that what we perceive as invisible forces are, in fact, fundamental threads weaving the tapestry of existence. Despite centuries of study, our current models of magnetism are still approximations, tools that allow us to predict and manipulate magnetic effects without fully explaining their deepest origins. Classical physics, particularly Maxwell's equations, elegantly describes how magnetic fields interact with electric currents and changing electric fields, enabling engineers to design everything from electric motors to MRI machines. Yet these equations do not answer the fundamental question of why electrons themselves generate magnetic fields or how their intrinsic properties, such as spin, emerge from the underlying laws of nature. Quantum mechanics provides part of the answer, describing how the probabilistic behavior of electrons and their interactions give rise to magnetic phenomena at the microscopic scale. However, even quantum theory leaves open questions, especially when it comes to complex materials and exotic states of matter. In some materials, electrons interact in ways that create unexpected magnetic behaviors, such as spin frustration or emergent magnetism in quantum materials, phenomena that cannot be fully captured by traditional models. This gap between prediction and understanding highlights the limitations of our current frameworks, reminding us that our scientific knowledge is always provisional, a stepping stone toward deeper insight. The challenge is not merely academic, it has practical consequences, as developing more advanced magnetic materials or quantum technologies depends on a richer understanding of the principles at play. Researchers continue to explore new theoretical approaches, combining classical, quantum, and computational models, striving to uncover a unified explanation that reconciles macroscopic observations with microscopic laws. This ongoing quest demonstrates that magnetism is not a solved problem, but a living mystery, one that challenges our comprehension of nature's fundamental workings and inspires scientists to look beyond established theories in search of the hidden truth underlying the forces that govern our universe. Magnetism is not only a subject of scientific curiosity, but also a cornerstone of modern technology, revealing its hidden power in ways that shape our daily lives and future innovations. From the devices we use every day to cutting-edge research, magnetic phenomena underpin countless applications. Magnetic resonance imaging, or MRI, relies on strong magnetic fields to peer inside the human body, allowing doctors to diagnose conditions with remarkable precision without invasive procedures. In transportation, maglev trains use magnetic levitation to float above tracks, reducing friction and enabling speeds that would be impossible with traditional wheels. On the microscopic level, advances in data storage and electronics harness the alignment of magnetic domains to encode information, making modern computing and digital communication possible. In the emerging field of quantum computing, researchers exploit magnetic interactions at the atomic scale, using electron spin to represent quantum bits, potentially revolutionizing computation by solving problems far beyond the reach of classical computers. Spintronics, a branch of technology focused on manipulating electron spins, promises more energy-efficient devices and faster data processing, highlighting how a deeper understanding of magnetism could transform industries. Yet, despite our ability to harness these effects, the underlying principles of magnetism remain only partially understood. We can control and predict outcomes, but the fundamental origin of magnetic phenomena, particularly in complex and quantum materials, continues to challenge scientists. This contrast between mastery and mystery illustrates the dual nature of magnetism. It is both a tool that empowers human innovation and a phenomenon that reminds us of nature's complexity. Each technological application represents a step toward practical understanding, yet simultaneously hints at deeper layers of knowledge waiting to be discovered. The study of magnetism thus serves as a bridge between practical utility and fundamental science, showing that even forces we think we control are still filled with secrets that inspire curiosity and exploration. The mystery of magnetism challenges our very understanding of reality, revealing that even phenomena we take for granted are far more intricate than they appear. At first glance, magnetism seems straightforward. Magnets attract or repel, and magnetic fields guide compasses. Yet beneath these familiar effects lies a world of complexity, governed by quantum mechanics, relativity, and interactions that remain only partially understood. Magnetic phenomena emerge from the subtle behavior of electrons, their spins, and their interactions with one another and with atomic nuclei, forming patterns and effects that can seem almost magical. In certain materials, these interactions give rise to exotic states, like quantum spin liquids or topological magnets, where the rules of classical physics no longer apply, and particles behave in ways that challenge intuition. Even on cosmic scales, magnetic fields influence the behavior of stars, galaxies, and cosmic plasma, suggesting that magnetism is woven into the fabric of the universe itself. Scientists have developed sophisticated models and experimental techniques to probe these mysteries, from observing nanoscale magnetic domains to mapping interstellar magnetic fields. Yet every discovery opens new questions, showing how much remains unknown. This enduring mystery serves as a reminder that nature often hides its deepest principles, waiting for curious minds to uncover them. The study of magnetism is thus not just about understanding a force. It is about exploring the boundaries of human knowledge, confronting the limitations of our models, and embracing the uncertainty that drives scientific inquiry. Each experiment, each theoretical breakthrough, brings us closer to comprehending the profound principles that govern magnetic phenomena. But the journey is ongoing, revealing a universe that is more subtle, intricate, and awe-inspiring than our simplest observations suggest. Magnetism, in its mystery, teaches patience, curiosity, and humility, inspiring generations of scientists to look deeper and imagine possibilities beyond the visible and the known. In conclusion, magnetism is a force that surrounds us, shapes our world, and governs the universe in ways both seen and unseen. From the tiniest electron to the largest galaxies, it reminds us that even the most familiar phenomena hold mysteries waiting to be uncovered. Our understanding is still evolving, and each discovery opens new doors, showing that science is not just about answers, but about curiosity, exploration, and the courage to question what we think we know. As we continue to probe the secrets of magnetism, we are reminded that the pursuit of knowledge is a journey without end, where every insight illuminates the profound beauty and complexity of the universe. To everyone listening today, may your curiosity never fade, may your questions always lead you deeper, and may you embrace the unknown with confidence and wonder. Remember, the mysteries of nature are opportunities for growth and inspiration, and your pursuit of understanding can contribute to discoveries that change the world. Good luck on your journey of exploration, and thank you for sharing your time, attention, and curiosity. Keep questioning, keep learning, and keep reaching for the mysteries that lie just beyond our grasp.